Let me explain about the cell EMF. First of all, we should understand how to represent a cell. You please make a note of it. A cell can be represented, in this case I have taken a zinc copper electrodic cell. So here we have got the zinc electrode, that is the zinc electrode is dipped in zinc sulfate solution of certain concentration, and it can be simply represented as zinc slash zinc 2 plus, because zinc sulfate where you have got zinc 2 plus ion plus SO4 2 minus ion, but we take into account the zinc slash zinc 2 plus, because that zinc electrode is in contact with the zinc ion solution. Okay, and this double slash represents the salt bridge, and you have got the copper electrode, copper solution, that is copper sulfate solution, and that is in the aqueous form. So aqueous solution of zinc sulfate solution and the aqueous solution of copper sulfate, and simply it can be represented in the ionic form. So slash copper, so it means a zinc electrode is dipped in zinc ion solution, copper electrode is dipped in copper 2 plus ion solution. So here, as I already mentioned, by convention you have to introduce the anode on the left side, cathode on the right side. So anode on the left side, cathode on the right side. We know very well, at anode oxidation takes place, at cathode reduction takes place. So these are all the basic ideas based on which let me proceed now. And this double slash represents the what? Salt bridge. Okay, right. Now the cell EMF is nothing but it is represented by this important equation, that is E right minus E left. Okay, we can make use of this equation. So as I already mentioned, here I have the anode on the left, so E left, E right. Now what is the E right value? 0.34, left minus 0.76. So what is the cell EMF? This E right minus E left, that is 0.34 minus of minus 0.76, and that is given here as cell EMF. When I put E naught, that represents what? The standard cell EMF. Okay, right. Now let me go ahead. So the electrode potential here, it is represented by the Nernst equation. The electrode potential of an electrode, that is potential at an electrode. We used to talk about the origin of electrode. Let me consider I have got a bath here, and I have given the electrolyte here. This is the electrolyte. I have dipped one electrode. So what happens here? By dipping this electrode, it arises some potential. Okay, so there arises some potential, and that potential is called electrode potential. So if the electrode is cathode, it is called cathodic potential. If the electrode is anode, it is called anodic potential. So what is cell EMF? The potential difference, the difference between the right electrode and the right electrode potential. Okay, so usually cell EMF can be represented as E, capital E, whereas electrode potential can be represented as E in this way. Okay, now let us follow that convention, and the electrode, a single electrode potential can be that is determined by using this Nernst equation. So this Nernst equation states that E, the electrode potential, is equal to E naught, the same electrode at the standard state. It is called standard electrode potential, minus 2.303 RT. R is the gas constant value, and T is the temperature in Kelvin, divided by NF. N is the number of electrons transferred during the cell reaction or electrodic reaction. In this case, electrodic reaction. Suppose 2 electrons are transferred, means you have to introduce N is equal to 2. Faraday, F is given by 96,500 coulombs roughly, or 96,495. You can round it off as 96,000. So 96,500 coulombs, and here F is nothing but the charge carried by 1 mole of electron. How to represent 1 mole of electron? How many electrons are present in 1 mole of electron? Avogadro's number of electron. Therefore, what do you mean by F? F is equal to Avogadro's number into charge of 1 electron. What is the charge of 1 electron? What is the charge of 1 electron? 1.6 into 10 power minus 19 coulomb. So look at this equation. Here I have given F is equal to N into E, where N is equal to Avogadro's number, that is 6.02 into 10 power 23, and E is the charge carried by 1 electron, that is nothing but 1.6 into 10 power minus 19 coulomb. So that is given as 96,500 coulomb per mole. So it is nothing but the charge of 1 mole of electrons. So Faraday is nothing but the charge carried by 1 mole of electrons. How many electrons are there? Avogadro's number of electrons. What is Avogadro's number? 6.02 into 10 power 20. So likewise, and finally we get 96,500 coulombs approximately. So one F means what? 96,500 coulomb. Now, so here NF into log to the base 10. This is logarithm to the base 10 of 1 by m n plus. N plus is the charge of that metal ion. So here let me consider this electrodic reaction. It can be either anodic reaction or cathodic reaction. Okay. So usually anode potential can be represented in this way. For example, that is, you know very well, let me talk about the redox reaction. Redox reaction. Okay. So let me consider metal becomes metal n plus by removing n number of electron. So what is this reaction? Redox, oxidation or reduction? Oxidation. Why? Removal of electron. And where it takes place? At anode. At anode oxidation takes place. And then m n plus n number of electron gives m. It means it is reduction, is it not? So this occurs at cathode. Do you understand this? And that is why when we combine this, we are able to get redox reaction. So it is a spontaneous reaction as far as electrochemical cell is concerned. Okay. In the case of electrolytic cell, it is not spontaneous. We have to apply the current there. Okay. Right. So this anode and the electrode can be represented. See the anode. So anode is given on the right side. Is it not? I mean left side. M n plus. This is anode. Okay. And how to represent the cathode? The cathode should be represented as m n plus slash m. Do you understand this? So this is the way you have to represent the electrode. Okay. And how to represent the electrodic potential? Electrodic potential can be represented in this way. E. So when I put m plus, what does it indicate? This is the anode potential. Do you understand? How to represent the cathodic potential? E and then m n plus slash m. Do you understand? So what is this potential? Cathodic potential. What is this potential? Anodic potential. Okay. So this is reduction potential. This is oxidation potential. Now you should understand, we have got an electrochemical series based on the increasing value of reduction potential. So in India we follow only reduction potential because it will be of opposite charge if you interpret in anodic potential. Are you able to follow? For example, let me consider the electrode potential of, let me consider this one. See the copper electrode, this is reduction potential, it is a positive value. Okay. What about this? Why I have given negative value here? Because it is the oxidation potential. Okay. So oxidation potential actually, I mean truly speaking, the reduction potential of zinc 2 plus is 0.76 volt only. But since it is introduced as anode, it is given as minus value. Okay. So let us remember that we should go only by reduction potential. Okay. Right. And let me further continue. So the anode, so here let me consider the reduction. So Mn plus, as I already mentioned, that is we go by reduction potential, that is cathodic potential. So Mn plus n number of electron to give M as a solid one. Okay, this is the reaction. So in that case, now let us work out the equilibrium constant for this. We know very well what is equilibrium constant. Equilibrium constant, that is represented by what? K. Is it not? Now listen, I got A moles of A reactant, B moles of B reactant, and it sets up an equilibrium to give C moles of C product plus D moles of D product. So you can write down. So this is reactant and these are product. Okay. Now according to law of mass action, equilibrium constant is given by what is that? The product of what? Concentration of product. So C power C into D power D whole divided by the product of concentrations of reactants raised to the molar coefficient as power. So A and this is B. So this is given as what? The equilibrium constant. Okay, so according to law of mass action, there is a constant, and what is that constant? That is represented by equilibrium constant K. So which is nothing but the ratio between the product of the concentration of the product and the product of the concentration of the reactants. Okay, so let us consider in the case of metal reaction. Okay, I was talking about this cathodic reaction, is it not? So let us consider here Mn plus n number of electron. Okay, so let me write here M n plus n number of electron to give M solid. Okay, this is as solid. So what is the equilibrium constant for this? That is the product of the concentration. Actually the concentration of a solid one is 1. Active mass is actually we have to say active mass. So active mass of the solid is taken as unity, and for electrons it has no mass. Okay, you can neglect that. So the remaining is the concentration of Mn plus, or the active mass of Mn plus. Are you able to follow? So in place of K we can introduce, that is instead of log K we can introduce 1 by Mn plus. I hope now you should be able to understand how we are able to get this value. And then standard electrode potential, that is represented as E naught, and n number of electrons, as I already mentioned, F is this nothing but 96,500 coulombs. Now let me take the cell. In the case of cell we have got both electrodes, cathode and anode. So in that case let me represent the cell reaction like this. Okay, we already done the cell reactions for different types of batteries. Okay, so we have got the anode potential, cathode potential, then we combine to get the cell, and based on that cell you have to arrive at the product of the concentration of the product divided by product of the concentration rate, which is nothing but this one K. So here I introduced instead of K this value. So so this is the E cell. Okay, this is a Nernst equation for cell EMF. What about the previous one? That is the Nernst equation for electrode potential. This is for cell EMF, and here delta G. Now how we were able to, and I was talking about this already. Okay, right. We can also calculate based on the cell construction also. That is, as E cell is equal to, simply take the right potential, left potential, subtract it. Okay, right. And but truly speaking, actually that is this is E naught of a right, E naught of left. Okay, so why I introduce a minus sign? Because for reduction potential, if it is plus, it should be reversed. Okay, so for a simple understanding, we have simply taken E right minus E left, and here delta G is given as minus N of E according to fundamental laws of thermodynamics. What is delta G? Truly speaking, this is minus delta G. Minus delta G is equal to N of E. Okay, for example, I was talking about the chemical reaction is converted into electrical energy. Electrical energy is converted into chemical energy. So chemical energy is represented by the thermodynamic equation, that is free energy minus delta G means what? It is the natural or spontaneous chemical reaction. Okay, and what about NFE? NFE, that represents the electrical energy because it involves number of electrons, Faraday, cell EMF for electrode potential. Okay, so on the right hand side it talks about the what? It describes the electrical energy. And what about this? This is chemical energy. Okay, so both of them must be equal, and delta G is equal to, so this minus is taken here, so delta G is equal to minus NFE. And another equation is there for that is delta G. So minus delta G is equal to RT log K according to fundamental laws of thermodynamics. So that is also equated here. On left hand side you have got delta G. So the right hand side can be equated, and thereby you are able to get the Nernst equation. So this is the way of obtaining the Nernst equation. And instead of RT log K, I will explain about this. How this RT log K is converted here into what? 2.303, because natural log can be converted into log to the base 10 by multiplying by log what? 2.303 factor. Okay, so 2.303 RT divided by NF, and you are able to get the K value. You can substitute this. Is it clear? Okay, right. Then, so this is regarding cell EMF, and I wanted to explain further. Let me consider the zinc copper electrode. In the case of zinc copper electrode, I have got the zinc dipped in zinc 2 plus ion, salt bridge, copper 2 plus ion / copper. So this is the left hand side is anode, right is cathode. See, the potential, electrode potential is 0.34 volt, and here it is minus 0.76 volt. Okay, now at anode oxidation takes place, at cathode reduction takes place. So at anode means de-electronation, so I put a zinc 2 plus 2e. At cathode reduction takes place, that is addition of electron, so copper 2 plus 2e gives a copper. Now both of them have 2 electrons, so ensure both of them have equal number of electrons so that you can ultimately cancel the electron. Okay, so how many electrons are transferred here? 2 electrons are transferred, so you can strike out. Okay, so this can be combined as cell reaction, and in the cell reaction these are the product and these are the reactant. You know very well, when we talk about the concentration, the product or the concentration of the product means you have to consider only zinc 2 plus ion. Why we are neglecting copper being solid? Okay, so the active mass is 1, whereas here it takes the concentration, and similarly here zinc is 1, active mass of zinc is 1, and copper 2 plus is, that is the concentration. Okay, now what could be the value of K here, which is nothing but active mass of zinc 2 plus divided by active mass of copper 2 plus. Do you understand this? Right. And in other way, that is, we can simply substitute the values, okay, from the electrode potentials. So E right minus, all these values are available in the electrochemical series, which are arranged according to the increasing order of what? Reduction potential. Okay, right. So increasing or decreasing, it depends. Now so let me consider two values. For example, let me consider this is the reduction potential 0.34, this is the reduction potential, that is minus 0.76. So when the left electrode has got minus value of reduction potential, you should understand that it doesn't have the cathodic capacity. Do you understand? Because it has got the minus value, so naturally it cannot act as cathode as far as the other electrode is concerned. So likewise we can come to the judgment. Okay, if you have got two values, one value is less, another value, for example E1, E2, E1 is less than E2 means E2 acts as cathode, E1 is anode. Do you understand? And among these two values, which is lower, minus 0.76 is lower. It means it cannot behave as cathode because it is not a reduction potential. The negative sign indicates that is much less than that of anode, cathode, that is 0.34. So this acts as, so based on the value you can say whether the reaction is feasible or not also. Okay, so now minus 0.34 minus or minus 0.76, and we can combine this, so you are able to get the E cell value 1.1. So there are two ways to obtain this value. One is E right minus E left, another is by using Nernst equation. Are you able to follow? Is it clear? Right.